Hi, I'm Ben-Yaakov. This presentation is entitled Ideal Transformer, and it is in effect also an answer to a riddle that I've posted earlier about modeling of an ideal transformer. Now, in many cases, we like to model a transformer, which is basically a coupled inductor, and the way it's done is to have the leakages, then the magnetization inductance, and then we have this ideal transformer. And the questions were, what is the definition of an ideal transformer? What are the network equations of an ideal transformer? And how can an ideal transformer be modeled in SPICE or any other circuit simulator accurately, that is not in an approximate way? So let me start with the very basics. To my mind, an ideal transformer is really an embodiment of Faraday's and Lenz's law. Now, what is Faraday's law? It says that there is a relationship between the voltage imposed or generated by a coil and dφ/dt, the rate at which the flux is changing. On the other hand, Lenz's law says that if a change in a magnetic field of current I1 induces another electric current I2, the direction of I2 is opposite that of the change in I1. That is, if you have an induced current, then this current will oppose the original current, sort of cancel it out. We'll talk about it and the reason for that in a couple of slides later. So, if we have a two-terminal network, which represent the ideal transformer, there is an input, there is an output. Then, according to Faraday's law, if I'm putting here a voltage source, if there is a magnetic coupling, it'll generate a dφ/dt. Now, at the output terminals, we pick up some of this dφ/dt, or a larger amount, that is by the number of turns that we have in a transformer. So we have at the output side some k times dφ/dt. Now, since V1 is dφ/dt, V2 is k dφ/dt, obviously V2 is k times V1. This is Faraday's law. So this implies that I can put here now a dependent source. The dependency is on V1, it's k times V1. K is the amount of flux picked up by V2, the output terminal. Could be k, could be smaller or larger than 1. Now I'm going to put a load, a resistor. This resistor, due to the fact that it has a voltage on it, will pass some current, V2 over R. Now this current passing through this is, according to the Lenz's law, invoking a current here at the input terminal. This is the cause of this current, in a certain direction and a certain magnitude. So we understand that there's going to be a current here at the primary due to the current in the secondary. About the magnitude, the easiest way is just to go back to the conservation of energy principle, which means that V1 times I1 is equal to V2 times I2, from which we get that I1 must be k times I2. Lenz's law is in fact based on conservation of energy. This is why this coupling between the two currents. So now we understand that aside from the output dependent source, we have a current dependent source, and the value of which depends on the secondary current times this same k. So therefore, this is now the very basic model of an ideal transformer based on Faraday's law and Lenz's law, which means that we are going to have a dependent source at the output depending on the input Faraday's law, and then we have a current source at the input depending on the output current due to Lenz's law. Now, this is therefore the model. Once you have the model, there's no need to say there's no leakage, there's no loss, or it's not green, it's not red, it's not hot. That's it. That's what you have. Obviously, there are no losses because there's no resistors here. This is the very basic relationship of an ideal transformer. it is legitimate to ask what is the input impedance, say, under no load. Okay? Under no load, there is no output current. Therefore, there is no input current. So what you see here, there's no output, no input. You see an open circuit. You don't see large inductance. You see an open circuit. That's it. That's an ideal transformer. So now there is a question as to whether the ideal transformer is passing DC. Well, it does, because there is nothing here that says that this is only for AC. So all these relationships, this V2 KV1 and I2 1 over K I1, are holding for both AC and DC. So in the case of an ideal transformer, if you have DC at the input, you will have phi, which is now the integral of V1 due to Faraday's law. Phi will be going up, up and up, indefinite, because it's an ideal transformer. There's no limit. Obviously, in a practical transformer, there is a limit, which is B saturation of a ferromagnetic material. So therefore, the phi will be clamped to a certain value if you go on with it, which means that the slope will change, the phi dt will change, and therefore the voltage will drop. But for an ideal transformer, there is no limit, of course, and this can go up and up indefinitely. Now what happens if I'm trying to simulate a real transformer in a system? Say this is a converter, here's the transformer, here's the rectifier, and here is the ideal transformer representing the interconnection between the input and output of a practical transformer. Now, if I replace the ideal transformer with the two dependent sources, then obviously it's going to pass a current, both AC and DC, between the two terminals. Now, the point is that in the case of the input, normally we are going to have here a inductor representing L sub M, the magnetization inductance. The average voltage on this inductor is going to be 0. So therefore, there will be no DC current going to the other side, because the current will be passing here and there is a 0 DC voltage here. However, if there is some mismatch at the output and there are some converters, some rectification scheme in which you might have some DC passing through the transformer at the output, this will definitely pass to the input, and you will see it actually in LM in the simulation. So it's a little bit tricky here because of the passing of the DC. If you're trying to simulate a real system, it may give you some results which are not realistic in terms of the practical or real transformer. So there is another way, of course, which is well known, and that is to represent the ideal transformer by two coupled inductors. Now these now have to be extremely large as compared to the other impedances in the circuit, say a few henries or even more, and with a coupling coefficient of one, obviously without any resistances. So this is an alternative to the representation with dependent sources. So my answer to the question that I've posed are the following. What is the definition of an ideal transformer? I think that the best definition is that this is a two-terminal or more network embodiment of pure Faraday and Lenz law. This leads to dependent sources. Now, what are the network equations of the ideal transformer? Obviously, these two basic equations, and which are correct for both AC and DC in the case of the ideal transformer. And how can an ideal transformer be modeled in SPICE or any other electronic circuit simulator? Well, accurately, it'll be by dependent sources. Approximately, you can do it with coupled inductors, and the inductances being very large. So this brings me to the end of this presentation. I hope you found it of interest, and perhaps it'll be useful to you in the future. Thank you very much.